the sample problem. It says the cross-section of the long conducting cylinder with inner radius A equals 2 centimeter and outer radius B equals 4 centimeter. The cylinder carries current out of the page, and the magnitude of the current density in the cross-section is given by J equals ZR squared, with C equals 3 times 10 to the 6 A per meter to the 4th power, and R in meters. What is the magnetic field? B at a point that is 3 centimeter from the central axis of the cylinder. Okay. So let's see. So here we will consider the magnetic field at 3 centimeter from the center. And actually A is 2 centimeter, B is 4 centimeter, which means 3 centimeter is Y between A and B, Y between A and B. So here we consider the impedance loop to be here with a radius R to be 3. And actually we need to calculate the I enclosed in this part, because there is only a current in this part inside the impedance loop. And of course, part of the current is outside the impedance loop, but we don't count it here. Okay, so here we have I enclosed. I enclosed will be J dot dA, and of course J and dA are perpendicular to each other, so it is nothing but J times dA. And here we consider the current is into the page, out of the page. Out of the page. The current is out of the page. So this is the current direction. And here it defines the ampere to be clockwise. So this one is clockwise. And using the right-hand rule, you know, if you use a forefinger, follow this direction, your thumb will be pointing into the page. So into the page is the direction of positive, which means that the current is a negative current for this Ampere's law. Okay, so in this case, we will consider J will be a negative value. So we have a negative dr squared. And then dA is r dr d theta. So we have a r dr and then d theta. Theta is the whole circle, so which means it is from 0 to 2 pi. And then r dr, we should integrate from, this is small a, to r. So we probably should make it r prime here for the dummy variable. Yeah. So we have negative d, and then here we have r prime cubed dr prime from a to r. And then this is 0 to 2 pi d theta. So this one is negative c. This is r to the 4th power over 4. So we have r to the 4th power over 4 minus a to the 4th power over 4. And then this one is nothing but 2 pi. So the answer will be, so this is only the minus pi over 2, minus pi over 2, because 2 and this 4 will be cancelled. So we have 2 here. And we have c times r to the 4th power minus a to the 4th power. And okay, so we have this I enclosed. So we move it here. I enclosed is nothing but negative pi over 2c, and then r to the 4th power minus a to the 4th power. Then we can continue with the Ampere's law. Ampere's law, so we have the line integral on the left side, and then on the right hand side we have mu 0 I enclosed. So on the left side, we still have 2 pi r times B. And then for the right side, we have mu0 times negative pi over 2c times r to the 4th power minus a to the 4th power, like this. So B will be, we can see pi and pi can be cancelled. And then it becomes minus mu0 c, mu0 c. And then we also have these two. And then here we have 2r. So we have totally 4r. And then, of course, we still have this term, r to the 4th power minus a to the 4th power. So we can just plug in the values. Mu0 is 4 pi times 10 to minus 7. So cancel with this 4 will be negative pi times 10 to negative 7. And then times c is this one, 3 times 10 to the 6th power. 3 times 10 to the 6th power over r. R is 3 centimeters, 0.03. And then this is a 0.03 to the 4th power minus a is 2 centimeters, 0.02 to the 4th power. So this one is negative 20 mu Tesla, 20 mu Tesla, which means this is negative. This is negative. And we define the impedance loop to be clockwise, which means that this is negative, and which means the magnetic field is counterclockwise. Counterclockwise. Yeah, here we define the impedance loop to be clockwise, and if it is negative, then it should be counterclockwise. And if originally you can define the impedance loop to be clockwise, if you define the impedance loop to be clockwise, then you don't have this negative sign here, because if you define the impedance loop like this, then you use a right-hand rule, then you will have if you define the impedance loop to be counterclockwise, if you define the impedance loop to be counterclockwise rather than clockwise, then this is the positive direction. And in that case, the current will be considered to be positive. So this case, I enclosed is positive. I enclosed is positive. And finally, of course, you can find the B to be positive. And then if B is positive in this case, which means it is clockwise. So it doesn't really matter you define the impedance loop to be clockwise or counterclockwise. If you can come up with the polarity correctly, then it will be the same. So you don't really need to bother about whether we need to assume it to be clockwise or counterclockwise. Both of them will give you the same results. Okay, so next we talk about this one is called a solenoid, which is actually an inductor. If you have learned the circuit analysis, it is nothing but an inductor. Okay, here it says the solenoid's magnetic field is the vector sum of the field produced by the individual terms windings that makes up the solenoid. So you can see the solenoid is nothing but this. Solenoid carrying current I. And here you can see a very messy graph here. So you can see the green line are the magnetic field lines. So you can see there are several groups. One group is like this, which is like a magnetic dipole, And also, if you consider the region close to the wire, then you can see something like this. And of course, for the outer part, the magnetic field will be much weaker. So it says for the points very close to a turn, the wire behaves magnetically almost like a long straight wire, and the line of E are almost concentric circle. For this part, it means this case. Although it is not a long straight wire, but yeah, it is approximately like if you only consider the very small region close to the wire, then you can simply assume that it is something like a long straight wire, but of course a bending long straight wire like this. Okay, so the field tends to cancel between adjacent turns, because as you can see here, for this turn is clockwise. This turn is also clockwise. So for the point right between this here, so this one is pointing downward, this one is pointing upward, so they will be cancelled. So, and as you can see here, the electric field line in between will be much sparse. You can see the line here is dense. Here is still dense, and for the middle part, there's low electric field magnetic field lines, which means that the magnetic field there will be weak. Okay, so at points inside the solenoid and reasonably far away from the wire, B is approximately parallel to the solenoid axis. So which means this part. So this part, which is farther away from the wire, which means the right in the middle part of the solenoid, then you consider the magnetic field is pointing to the right side in this case. If you consider the current in this direction, this is going into the page, this is going out. So the current is like this. And then you use your right hand rule, you can determine, use the forefinger following this direction, and then your thumb will be pointing to the right side, which refer to the direction of the magnetic field. And we will approximately assume the magnetic field inside the solenoid to be uniform, at least farther away from this wire. Okay, so let's see the derivation here. So let us now consider Ampere's law to the ideal solenoid. So this is the cross section of the solenoid. So we try to cut this one like this. So we can see something like that, because this is going into the page. So at this point, we'll be going out of the page. At this point, we'll be going out of the page. And so as this one, so on and so forth up to the last one. And here, for every cross section, you can see the current is going into the page. So finally, the cross section area will be something like that, going into the page all the way for the bottom row, and for the top row, this is the current is going out of the page. So it is like something like this. Of course, it is going from here to there and then going back to here. But yeah, we only consider the cross section here. Yeah, so here it makes some simplification to make it feasible to derive the expression. So here it assumes that the B is uniform inside the solenoid and 0 outside. So there is no B field outside, although there should be some, although much weaker than the inside part. But here it only assumes that the magnetic field outside is 0. So using the rectangular impedance loop, ABCDA, ABCDA, so this rectangle. Okay, so of course, for the impedance law, we need to consider the line integral, the closed line integral. So B dot ds from A, B, C, D to back to A, we can separate into 4 parts, from A to B, from B to C, from C to D, and from D to A. And then we separate into 4 line integral, which is not closed. So this is closed, which refer to the closed line integral. But here, this is only a open path from A to B, from B to C, so on. So we don't have a circle here. Okay, so for DA and also BC, for DA, BC, it is perpendicular to the magnetic field. So this one, and this one and this one will be nothing but 0. And for CD, we also assume the magnetic field outside the solenoid to be 0. So this term is also 0. So for these 4 terms, 3 of them will be 0. And the only remaining one is the B dot ds from A to B, And we also assume that the magnetic field is uniform. And of course, it is parallel to the B field. This part is parallel to the B field. So which means that the angle between this is ds and the B will be 0 degree. So B dot ds is nothing but BDS, and B is uniform. So it is nothing but BDS from A to B, which means this is the length of AB, which here we call it H. So we have B times H here. Okay, so for the impedance law, on the left side, we have B times H on the left side. And for the right side, we have mu naught I enclosed. So here, we have many I pointing out of the page. And as you can see here, the impedance loop is counterclockwise, which means that the positive direction will be out of the page. If you use your 4 fingers following this direction, your thumb will be pointing out of the page. And all of the current here are pointing out of the page. So they consider to be positive current. So this I enclosed will be, or maybe we can simply rearrange this one here. So we have B equals mu naught I enclosed over H. I enclosed over H. So we have mu 0 I. So all the current will be I because it is solenoid, it is an inductor. So all the current will be the same. And here there will be many wire here. So or many turns here. So we assume there will be n turns over H, n terms over H. But here it use small n to, this small n means capital N over H. So n, capital N is the total number of turn here, The H is the length, here, which means that n is the number of turn per unit length. N is the number of turn per unit length. So in these 2 chapters, we usually use the capital N to refer to the number of turns, or total number of turns. And here, it refers to the number of turns per unit length. Okay. So finally, n. So we have mu 0 I small n like this for the solenoid. So it says mu 0 is a constant. I is the current. N is the number of turn per unit length, which means that if you want to have a larger magnetic field, then you can either increase the current, or you can increase the number of turn per unit length. Okay, so next we talk about another one called the toroid. The toroid, which means that originally you have a solenoid, and then you connect the end to the front, so make it a loop, so it become a toroid. So a toroid may be described as a hollow solenoid that has been curved until its two ends meets, form a sort of a hollow bracelet, a Solenoid. So from the symmetry, we can see that the line of B form concentric circle inside the toroid. Concentric circle inside the toroid. So let us choose the concentric circle of the R as an ambient loop. So this orange circle is the ambient loop, and here for the inner circle, we have all the current going into the page. For the outer circle, we have all the current going out of the page. So now we consider the ambient loop here, which means that only the inner circle has the current enclosed by this ambient loop. So we only count the current for the inside circle. So now let's choose a concentric circle and traverse is in the counterclockwise direction. Yeah. So the Ampere's law use B. The Ampere's law is still B dot ds, the line integral, equals mu naught I enclosed. Okay, so B dot ds, we still have a B times 2 pi r as before, and mu naught I enclosed is all the I here. So everyone is small I, and then you need to multiply it by the total n, total number of turn here. So it is I capital N. So finally, we have a B times mu naught I n over 2 pi r. So in contrast to the situation for the solenoid, B is not constant over the cross section of a toroid. So because here mu 0 is a constant, I is a constant also, and then capital N you cannot change, is the total number of turn here, and then 2 pi is of a constant. But it means that B is inversely proportional to R, which means if R is smaller, then the magnetic field is stronger. So this is the magnetic field generated by the toroid. Okay, so let's see a sample problem here. It says a solenoid has a length L equals 1.23 meter, inner diameter D. It carries a current I equals this one. So it consists of 5 close pack layers, each with 850 turns per length. What is the B at this center? So here we consider a solenoid. So we only need to consider B equals mu naught times I and small n. Small n is the number of turn per unit length. So this is 4 pi times 10 to minus 7 for mu 0. And then I here is this one, 5.57. And then small n. Small n will be, we all together have 5 pack. So 5 times 850, because each pack has 850 turns along length L. L is 1.23. So this is the number of turns per unit length for a single pack. And then we altogether have 5 packs, so we need to multiply by 5. So finally, we have a 2.42 times 10 to minus 2 power Tesla, like this. Okay, so this is simple. Yeah. So next, we talk about the current carrying coil as a magnetic dipole, which is similar, which is actually has the same form as the electric dipole. Here we can see 1 over 4 pi epsilon naught 2p over c cube. Let's see, E equals 1 over 4 pi epsilon naught P is the dipole, electric dipole moment, and then over C cube. Okay, so as you can, we still have a factor of 2 here. So in this case, as I mentioned, this is the duality. So now we can just change E to B, and then change the electric dipole to magnetic dipole. And then also we change epsilon naught to 1 over mu naught. Okay, so finally we will have E becomes B, and then 4 pi doesn't change. And then epsilon naught to be 1 over mu naught, so mu naught go to here. And then 2, P becomes mu. Electric dipole moment becomes a magnetic dipole moment. And then we still have C cube here. So this one is actually this one. Of course, 2 and this 2 cancel. You have a 2 pi here. Okay. And here is that. So if you have a current carrying wire, which is actually the same as having a magnetic bar here, it doesn't really mean that we have both. We have both this current carrying loop and also the magnetic bar at the same time. It only tells you that if you have this one, if you have this current carrying wire loop, it is actually the same as having a magnetic bar here. It will generate the same magnetic field. Okay. So here it talks about the current carrying coil as a magnetic dipole. So we have 2 ways in which we can regard a current carrying coil as a magnetic dipole. It experiences a torque when we place it in an external magnetic field. So I think previously we have already talked it in chapter 28. Yeah, in chapter 28 we are already talking about this part. So the torque will be N, will be something like N times. This one is NIA is nothing but mu. NIA is nothing but mu. So we have a mu cross B, something like that. Actually, we have talked it before. So it generates its own intrinsic magnetic field given for distant point along its axis. Yeah. So from the magnetic point of view, this loop and the magnetic bar are actually the same. So here is a simple derivation. This is not rigorous in mathematical sense, but yeah, actually there is something like that. If you need to consider it rigorously, you need to use the Biot-Savart law to derive the whole equation. So here we have a loop here. And of course, we only assume there's only a single loop. But if we have n loop, then you need to multiply by n, which is nothing special. We usually just merge this term into the magnetic dipole moment. So here for the Biot-Savart law, it is like that. And this is ds pointing out of the page. And then out is from this point to point P we concern. P is on the z-axis, which is a perpendicular line going through the center of this circle. Okay, so cosine alpha is this one. Cosine alpha is the capital R over small r, and small r is a square root of z squared plus capital R squared, like this. So this is cosine alpha. This is r, and then we can plug these two into here. So we still have this r squared to the z squared to the 3/2 power, and then do this integration. This integration is easy because this is nothing but a constant. So we only integrate ds over the whole circle, which is nothing but 2 pi r. So this is so this one, integration of ds is nothing but 2 pi capital R. So we cancel some of it, 2 pi here, and then we have R squared here. And finally, if we assume z is much larger than capital R, then we can slightly rearrange the term like this. Because z is much larger than R, so we can just drop this term. So we only have a z cube here. And then we can multiply by pi and divide by pi, because it is a cross-section area of the circle. And then IA will be mu. If we only have a single term, then n is 1. And of course, you can also put the n here. So NIA is the mu. So we have mu over 2 pi and then mu 0 c cube, like this. So this is a derivation of this equation. Okay. So finally, we have two simple sample problem. Additional problem. Let us finish it quickly. So here it says two circular arcs have a radius A, B, and then this angle theta is 74 degrees. So the current I. So what are the magnitude and direction of the magnetic field at point P? Okay. So this is a shape. This shape. So we have 4 parts: 1, 2, 3, and 4. So you can simply imagine for part 1 and part 3, it will generate no magnetic field at point P because this one is going through this point. And for part 2 and part 4, this one current going to this side, and this one the current going to this side. So using the right hand rule, for part 2, the magnetic field is pointing into the page for part 2. But for part 4, it is pointing out of the page. And the distance from part 4 to the center is smaller. So you can also imagine B4 will be larger than B2. So B is nothing but mu 0 I theta over 2 pi. B is smaller. So the whole term will be larger. And then minus B0 I theta over 2 pi A. A is larger. Okay. So here we have mu 0 I over theta over 2 pi, and then 1 over B minus 1 over A. And then we can plug in the value. So mu 0 is 4 pi times 10 to minus 7. So partly cancel with the 2 pi, so it becomes 2 times 10 to minus 7 times I is 0.411 times this one, 74. 74.0 degree over 180 degree times pi is the angle in radian. And then we have a 1 over 0.107 minus 1 over 0.135 here and here. Okay, so next, the answer will be 1.02 times 10 to minus 7 Tesla. and of course the direction. So for part 4, is larger. So this is pointing out of the page. Okay, so this is for part B. This is for part A. Okay. And then the next one. Yeah. Okay. So here it says we have a long circular pipe with outside radius 2.6 centimeter, and then this is also out. This is also out. This is a wire. The wire has and then this one has a uniform current going into the page. So we have some cross here, and then a wire one parallel to the pipe at a distance 3R. So this is totally 3R from the center to center. And it asks what is the magnitude and direction of this current, such that the net magnetic field at point P, at this point, which means that BP has the same magnitude as the net magnetic field at center pipe, which means this is C, BC equals BC. The magnitude will be the same, but the direction will be opposite, which means BP equals minus BC. Okay, so BC here will be BC here will be mu 0 IW. IW is the current of the wire, IW, over 2 pi. So we have altogether 3R. So we have 3R here. And then for this one, it will generate no magnetic field here, because you can simply imagine this part, the B field is the current is going into the page. It's coming into the page. It will cancel the B field generated by this part, because when you consider the cross product, they will actually cancel each other. So this ring will not generate any B field at the center point. So this is nothing but mu 0 IW over 6 pi capital R. And for BP at this point, so we have mu 0 IW over 2 pi R, because this one is only R. This one is 2R. So we have a negative mu 0 I over 2 pi times 2R. Okay, so altogether it will be mu 0 IW over 2 pi R minus mu 0 I over 4 pi R. And suppose we have this expression, we will have mu 0 IW over 6 pi R equals mu 0 I over 4 pi R minus mu 0 IW over 2 pi R. So finally, after some simplification, algebraic simplification, we will get, because mu 0 we cancel, pi will be cancelled, r will be cancelled. So the only remaining stuff is I and IW. So finally, it becomes IW equals 3 over 8 I, which is 3 over 8 times 8 milli, so times 8, so which is 3 milli 8. 3 milli 8. And and as much as this is into the page, this is positive, so this is into the page. Okay, so this is the end of this chapter, and I'll see you next week.